Hi, welcome everybody to this small and brief presentation about how the heat affects buildings and in this case Can Maragall. To get started, we're gonna explain what is the heat transfer, when occurs and why, as how to calculate it, and finally, how it affects the traditional house we're studying, that is Can Maragall. The heat transfer is the step of the thermal energy through a material, from a space to another one with a different temperature. So, in order to have a heat transaction, the two spaces need a variation of temperature. There are three ways on which the heat is transferred: through convection, radiation, or conduction. The first way is the convection, that is, the transfer of heat between gases and solids. An example of this phenomenon would be the interaction between the hair drying and the hair. Another way of transferring energy is the radiation, where a body emits energy from its surface through heat waves. An example of this would be interaction between the kitchen stove and a pen. The last one is the conduction, where the heat is transferred all the way the length of a body from a heat source to a cold space. An example from this would be the interaction between a naked feet and a cold floor. When we want to study the heat transfer of a building, we first have to calculate the thermal flow, or heat flow, that arrives through the walls, through the floor or through the roof. To calculate this flow that appears when there's a temperature difference between two zones of the same material, we follow this formula, where T2 and T1 are both different temperatures of the material, D is the width of the material, and K is the thermal conductivity, a property all materials have. Once we have the thermal flow, we are able to calculate two things that help us understand the heat transfer process. The first one is the total power, expressed by the letter P, that increases or decreases depending on the thermal flow. To calculate this power, we multiply the thermal flow for the surface affected by the heat, as seen on the following formula. The second thing we can calculate is the energy consumption of a determinate interval of time, which means that the formula is the total power multiplied by the time interval. The thermical isolation is the direction of heat transfer between objects in contact or between two spaces with different temperatures. With a well-isolated building, we can easily regulate the temperature inside it to get a comfortable environment. A good thermical isolation has a high thermal capacity, capable of conducting high temperatures with ease, without getting damaged. The formula to calculate the coefficient of thermical isolation of a material is this one, where C is the coefficient and the variation of Q is the variation in energy divided for the variation of temperature. Another section of the laws of thermodynamics in the building is the loss of calorific energy that occurs when there is a lack of thermal insulation. In each house or housing, the losses are different, and a study of a specific thermal insulation should be carried out to know the heat energy losses. However, on average, in a house, it loses 35% of energy through the facades, 25% by the ceilings, 50% for land, and finally 25% for the doors, windows, and filtration of air. Having your house well isolated is a really important thing to do if you want to live in a comfortable space. Not only does the isolation help keep you a control over the temperature of your house, but also reduces the energy loss of the building, because the isolation panels make it harder for the energy to escape to the exterior. As an old and traditional building, it doesn't have any dedicated isolation, and instead relies on passive cooling on isolation thanks to its massive external walls. The building is made mostly of rock and ceramic, what means that the interior is cool on summer and cold on winter. Heat transmission is different depending on the material we use in the construction, since each material has its value for thermal conductivity. For example, in the materials of the house of Can Maragall, the thermal conductivity of bricks is 0.7 watts divided meter per Kelvin. So the thermal conductivity of lime and cement mortar and wood is not that great. On the other hand, the position of the material in the design of the construction is also important for the correct functioning of the envelope, avoiding condensation problems. In this case, we can affirm that Can Maragall is not the best isolated house, but that is obvious because it's a really old structure. It was made to be cool on summer and cold on winter, thanks to the huge walls and floor of rock and ceramic. We can reduce the heat loss through different strategies. We can use low emissivity material to avoid heat loss by radiation. We can create natural ventilation by ventilation, or we can use low emissive glass in windows to reduce the demand for heating in winter. The thermal inertia of the materials that make up the thermal envelope is a good strategy for controlling energetic demand in indoor spaces, in certain areas, especially in climates with a variation in significant temperatures between day and night. Thermal inertia provides passive heat accumulation capacity. The outer temperature and direct solar radiation heat the outer surface of the construction element during the hours of sunshine, which makes that this accumulated heat begins to transmit slowly inwards. This implies that you can take advantage of the accumulated heat when the temperatures drop at night. And finally, here are all the digital resources that we use in the making of this small project. And well, here concludes our presentation. Thanks to everyone for listening, and we hope you all learned something new today.